Our home stretches far beyond the Milky Way into a web of 100,000 galaxies. This is the Virgo Supercluster, a neighborhood of staggering scale and profound mystery. Within its immense boundaries, astronomers are confronting cosmic puzzles that defy our current laws of physics. By the end of this exploration, you will understand the 25 greatest enigmas shaking the foundations of modern science. How can a jet of matter appear to move faster than light? And why are galaxies vanishing from vast regions of space? Each unanswered question is a frontier waiting for a pioneer. What does it feel like to stand at the edge of such a deep and sprawling unknown? At the very heart of this supercluster lies its namesake, the Virgo cluster itself. This dense knot of over 1,000 galaxies acts as a gravitational anchor for our entire local cosmos. Yet even here, in a place we can observe with relative clarity, a fundamental piece of the cosmic inventory is missing. This is the Virgo cluster's missing baryon problem. Baryons are the ordinary matter that makes up everything we can see and touch, from stars and planets to you and me. Based on the immense gravity of the Virgo cluster, which comes from both dark matter and this normal matter, scientists can calculate how much baryonic stuff should be there. But when they add up all the visible stars and the hot gas they can detect, the numbers do not match. A huge portion of the expected normal matter is simply gone. Where could it be hiding? The leading suspect is something called the warm-hot intergalactic medium, often abbreviated as WHIM. Picture the vast spaces between galaxies in the cluster not as perfect emptiness, but as a faint, superheated fog. This fog is made of gas so tenuous and so hot that it is nearly invisible to most telescopes. It does not glow brightly in visible light like a star, nor does it shine with the intense X-rays of the ultra-hot gas at a cluster's core. It exists in a difficult-to-detect middle ground. Finding this missing matter is like trying to spot a single, dim light bulb in the fog across an entire city. Scientists are hunting for this elusive WHIM using space telescopes sensitive to specific types of light. The Chandra X-ray Observatory looks for extremely faint X-ray signatures, while the Hubble Space Telescope and others scan in ultraviolet light, searching for the subtle absorption lines this gas creates as it filters the light from distant quasars. Each observation is a painstaking effort to map an invisible component of our universe. Solving this mystery is not just about accounting for lost material. It is about understanding the complete life cycle of matter in the cosmos. How did so much of the universe's normal building blocks end up in these hard-to-find places? The answer is woven into the very fabric of the supercluster, waiting to be pulled into the light. That missing matter is a ghost hiding in plain sight, but some corners of the supercluster are quiet in an entirely different way. Drift away from the crowded Virgo cluster and you can find a place of profound stillness known as the Fornax Void. In a universe woven together by filaments of galaxies, a void is a bubble of relative emptiness, a cosmic desert. Yet the Fornax Void stands out even among deserts. It is exceptionally, puzzlingly quiet. While most large voids still contain a handful of scattered galaxies, this region appears to be almost completely barren. The question is simple and haunting. Is this void truly empty, or are we just not seeing what is there? The silence could be an illusion. Perhaps the void is populated by countless dwarf galaxies, small and faint, their light too dim for our current telescopes to catch from such a distance. These galaxies would be made mostly of dark matter, with only a sprinkling of stars, making them cosmic ghosts drifting in the dark. If that is the case, then the Fornax Void is not a true emptiness but a realm of shadows. The other possibility is far more intriguing. What if the void is genuinely, profoundly empty? This would challenge our understanding of how the universe arranges itself on the largest scales. After the Big Bang, matter was not spread evenly. tiny quantum fluctuations grew over billions of years, amplified by gravity, into the web of clusters and filaments we see today. The voids are the inverse of that structure, the low points in the cosmic terrain. But a void as stark as Fornax suggests something may have pushed the process further. One compelling theory points to dark energy, the mysterious force accelerating the expansion of the universe. In the ancient past, as galaxies began to form, dark energy might have acted like a cosmic tide within these nascent voids. It could have provided an extra outward push, helping to evacuate the region more thoroughly than gravity alone ever could. This would have stretched the space inside the void, making it harder for galaxies to coalesce and leaving behind a cleaner, more absolute emptiness. The Fornax Void, then, is not just an absence, it is a laboratory. By studying its exceptional quiet, astronomers are listening for echoes of the universe's most dominant, yet least understood component. Is its silence the sound of things we cannot see? Or is it the signature of dark energy sculpting the cosmos on a scale we are only beginning to comprehend? The answer lies in the deep, quiet dark, waiting for a more sensitive ear. While voids whisper with the silence of absence, other regions of the supercluster scream with impossible energy. At the center of the giant galaxy M87, a monstrous supermassive black hole is firing a cosmic blowtorch directly at us. This is the M87 jet, a concentrated beam of matter and radiation stretching for thousands of light years. It is one of the most spectacular and studied objects in the Virgo cluster, yet it harbors a visual trick that once seemed to break the universe's ultimate speed limit. Observations show bright blobs within the jet appearing to move across the sky faster than the speed of light. This is called superluminal motion, and it is a breathtaking illusion born from relativistic physics. The jet is aimed almost directly at our line of sight. The material in those blobs is racing toward us at a significant fraction of light speed. As it travels, it is essentially chasing the very light it emits. From our distant vantage point, this creates a compounding effect, making the blobs appear to move sideways faster than they physically can. It is like watching a runner on a track who is also moving the finish line closer with each step. The apparent speed is an artifact of our perspective, not a true violation of Einstein's laws, but resolving that paradox only leads to deeper questions. The precision of the jet itself is a monumental puzzle. How does a chaotic, swirling maelstrom of infalling matter, a black hole's accretion disk, organize itself into such a narrow, focused beam? The process, known as collimation, must involve immensely powerful magnetic fields. These fields are thought to act like a cosmic funnel, twisting and channeling some of the infalling material away from the event horizon and accelerating it along the black hole's spin axis. Yet the exact mechanism that launches this material with such incredible force and keeps the jet so perfectly straight over vast distances remains unclear. It is akin to creating a laser beam from a volcanic eruption. Furthermore, we still do not know exactly what is being blasted into intergalactic space. The jet is undoubtedly composed of high-energy particles, but what is the mix? Is it mostly electrons and positrons, or are there heavier atomic nuclei being accelerated to near light speed? Determining this composition is crucial, as these jets are one of the primary ways supermassive black holes inject energy and influence the evolution of their entire host galaxy and the surrounding intergalactic medium. They are cosmic engines of feedback, and we are still learning what fuel they burn. The M87 jet is a brilliant, violent beacon. It shows us physics pushed to the extreme, where perspective warps reality and magnetic forces sculpt chaos into a beam that can be seen from millions of light years away. It is a reminder that even our most familiar cosmic speed limit can appear broken, not by magic, but by the profound and strange geometry of the universe itself. These brilliant jets are the fireworks of galactic collisions, but the aftermath of such violence leaves a more subtle and haunting signature. Between the bright galaxies of the Virgo cluster, there exists a faint, pervasive glow. This is intracluster light, a ghostly sea of stars adrift in the darkness. These are not stars born in the deep space between galaxies. They are refugees torn from their homes by gravitational tides during the colossal mergers and close encounters that shape a cluster's history. Picture the slow-motion collision of two galaxies, not as an explosive crash, but as a gravitational dance that pulls and stretches them like taffy. In this process, millions of stars are ripped from their galactic moorings and cast into the intergalactic void where they wander forever, untethered. This faint starlight should, in theory, be a direct record of the cluster's most violent events. Yet in Virgo, the story this light tells is confusing. The intracluster glow is both brighter and far more complex in its structure than our best computer simulations predict. It is not a smooth, uniform haze, but instead shows wisps, streams, and faint bridges connecting galaxies. These are the fossilized tidal tails of ancient collisions, visible long after the galaxies that created them have settled into a single, new entity. The sheer amount of this light suggests the Virgo cluster has experienced a more tumultuous, merger-heavy past than we once believed. Mapping this ghostly glow, however, is a monumental technical challenge. The light is incredibly faint, often over 1,000 times dimmer than the natural glow of our own night sky. It is like trying to study the delicate pattern of frost on a window while someone shines a car's headlights directly into your eyes. Astronomers must use incredibly sensitive cameras on the world's largest telescopes and employ sophisticated software to subtract the overwhelming light from the cluster's bright galaxies and nearby stars. Each observation is an act of cosmic archaeology, carefully brushing away the bright dust of the present to reveal the faint footprints of the past. The puzzling brightness and complexity of Virgo's intracluster light force us to reconsider the cluster's formation. Was it built through a few major mergers between large galaxies, or through a constant, chaotic reign of hundreds of smaller galaxies over billions of years? The answer is written in that faint glow, a palimpsest of violence that we are only now learning how to read. This ghostly starlight is a testament to the violent mergers that shape the Virgo cluster, but one of its largest galaxies hides a gravitational anomaly of its own. NGC 4472, also known as Messier 49, is a brilliant elliptical giant. At its silent heart lies a supermassive black hole, but this one defies a fundamental rule astronomers have come to rely upon. For decades, a tight correlation has been observed between a galaxy's central bulge of stars and the mass of its central black hole. The bigger the bulge, the more massive the black hole tends to be. It is a cosmic scaling relationship that suggests galaxies and their black holes grow together, co-evolving over time. Yet the black hole in NGC 4472 breaks this rule spectacularly. It is staggeringly overweight, possessing a mass far greater than the size of its galactic bulge would predict. This is not a slight discrepancy, it is a glaring outlier. How did this black hole become so overmassive? One compelling possibility is a hidden history of galactic cannibalism. Perhaps NGC 4472 devoured a sizable companion galaxy in the distant past. In that merger, the victim's own central black hole would have spiraled inward and combined with the giants, creating a single, supersized gravitational monster. The stars from the swallowed galaxy, meanwhile, would have been dispersed throughout the larger galaxy's halo, not necessarily adding to the central bulge we see today. This would leave behind a black hole that is, in effect, too big for its stellar home. Another, more unsettling explanation is that our measurements are wrong. Determining the mass of a black hole from millions of light years away is an exercise in extreme precision. Astronomers use a technique called stellar dynamics, carefully tracking the motions of stars whizzing around the galactic center. The speed of their orbits reveals the immense gravitational pull anchoring them, and thus the mass of the invisible object they orbit. Could there be something subtly skewing those measurements in NGC 4472? Perhaps an unseen structure or an unusual distribution of dark matter is influencing the stellar motions, making the central pull appear stronger than it truly is. The most profound possibility, however, is that the scaling relation itself is not the universal law we thought it was. This overmassive black hole could be a sign that in certain environments, like the dense core of the Virgo cluster, black holes can grow through different, more efficient channels. They might feast on vast amounts of gas funneled in by the cluster's dynamics, or undergo a series of rapid mergers, ballooning in size faster than their host galaxy can grow its central stellar population. NGC 4472's anomaly is a direct challenge. It forces us to ask if we have misunderstood the partnership between a galaxy and its dark heart. Is their growth a synchronized dance, or can the black hole sometimes sprint ahead, leaving its host behind? The answer lies in the silent, relentless orbits of distant stars, tracing the outline of a mystery that could rewrite a chapter of cosmic evolution. While black holes grow fat on mergers, the space between galaxies holds relics of a quieter, more ancient past. Far from the dense Virgo cluster, in the neighboring Leo group of galaxies, there drifts a structure that seems out of time. It is called the Leo ring, a colossal, faint loop of hydrogen gas nearly 650,000 light-years across. To put that in perspective, it is a ring of gas so vast it could comfortably contain our entire Milky Way galaxy several times over, and it orbits not one but two large galaxies. What makes this ring so profoundly puzzling is its appearance. It looks primordial, a simple cloud of almost pure hydrogen and helium, the basic ingredients forged in the Big Bang. It lacks the heavier elements, the metals that are forged inside stars and scattered by supernova. This pristine quality suggests it could be a cosmic fossil, a leftover cloud from the very formation of the supercluster that never collapsed to form stars. It is as if we found a perfectly preserved, untouched block of marble from the dawn of the universe, just floating in space. But there is another, equally compelling story. This ring could be the spectacular debris from a violent galactic collision. When two galaxies pass through each other, their gravitational forces can pull out immense streams of gas, stretching them into great arcs and loops. This tidal debris would eventually settle into a structure much like the Leo ring. The evidence for this is in the ring's motion. Detailed observations show the gas is not static. It is swirling and moving in a complex dance that suggests a dynamic rather than a passive origin. So which is it, a primordial relic or a collision's aftermath? The ring's sheer size and its isolated, elegant structure argue for the relic hypothesis. It is too large, too symmetrical, and too chemically simple to easily explain as wreckage from a crash we can no longer see. Yet, the kinematic data, the story told by the gas's motion, whispers of a dramatic encounter. Astronomers are left with a cosmic detective story where the clues point in two opposite directions. Perhaps the truth is a strange mixture of both. Could a primordial cloud have been shaped and stirred by a later, gentle gravitational encounter without being polluted by heavier elements? The Leo ring hangs in the darkness, a silent question about beginnings and endings. It asks us whether we are looking at a building block that never found its purpose, or the beautiful, lingering scar of a catastrophe from ages past. That pristine ring of gas asks questions about the universe's raw ingredients, but to understand the cosmos we must also confront its most dominant yet invisible component. The standard model of cosmology, known as the Lambda CDM model, tells a compelling story about dark matter. It says this mysterious substance, which neither emits nor absorbs light, forms the invisible scaffolding of the universe. According to powerful supercomputer simulations, dark matter should clump together under its own gravity, creating halos around galaxies with a very specific shape. At the very center of these halos, especially around small dwarf galaxies, the simulations predict a steeply rising density, a sharp peak called a cusp. Imagine a mountain with a sharply pointed summit where the dark matter is most densely packed right at the galactic core. This is what our fundamental physics tells us should exist. But when astronomers look at real dwarf galaxies within the Virgo Supercluster and elsewhere, they see something profoundly different. By carefully measuring how stars and gas rotate around these galaxies, they can map out the gravitational pull and thus the distribution of the unseen dark matter. The data consistently reveals not a sharp peak, but a gentle, flat central region, a core. It is as if the mountain's peak has been sheared off, leaving a plateau. This glaring mismatch between theoretical prediction and observational reality is known as the core cusp problem, and it represents one of the most significant cracks in the foundation of our standard cosmic model. How can our simulations, which so beautifully reproduce the large-scale cosmic web, fail so dramatically on the scale of individual small galaxies? One leading line of investigation points not to dark matter, but to ordinary matter. This is the theory of baryonic feedback. Dwarf galaxies with their shallow gravitational wells are highly susceptible to the violent effects of star formation. When many stars are born in rapid succession, their intense radiation and powerful stellar winds, followed by supernova explosions, can blast gas outward with tremendous force. This energetic outflow could literally push against the dark matter, scouring out the dense central cusp and smoothing it into a flatter core over billions of years. In this view, the core is not a failure of the dark matter model, but a signature of the complex, messy interplay between the dark and the light. The other possibility is more radical. It suggests our understanding of dark matter itself is incomplete. Perhaps dark matter is not completely cold and collisionless as the standard model assumes. What if dark matter particles can interact with each other through some unknown force, a concept called self-interacting dark matter? In this scenario, as dark matter particles swarm in the galactic center, their mutual interactions could transfer energy, effectively causing them to bounce off one another. This would prevent them from settling into an extremely dense cusp, naturally creating a softer, flatter core. The core cusp problem forces a fundamental choice. Are we witnessing the dramatic, previously underestimated power of stars to reshape their dark environments? Or are we seeing the first hints that dark matter has a rich, complex physics of its own? Each dwarf galaxy in the Virgo Supercluster is a natural laboratory testing these ideas. Their quiet, slow rotations hold the answer to whether we must revise our simulations of ordinary matter or our very definition of the dark universe that holds it all together. The quiet cores of dwarf galaxies hint at dark matter's secrets, but some cosmic objects take that imbalance to an extreme. Drifting through the dense coma cluster, part of the vast superstructure, is a ghost. Its name is Dragonfly 44, and it belongs to a class of celestial phantoms known as ultra-diffuse galaxies. These UDGs present a staggering paradox. Dragonfly 44 is physically as wide as our own Milky Way, a colossal expanse of space. Yet when you look at it, you see almost nothing. It contains roughly 1% of the stars our galaxy holds, making it so faint it was only discovered in recent years by a specially designed telescope array. It is a cosmic skeleton, a vast framework with almost no flesh. The mystery deepens when astronomers measured how its few stars move. Their high orbital speeds revealed a gravitational anchor of unbelievable mass. Dragonfly 44 is not just a faint galaxy, it is a dark matter fortress. Over 99% of its total mass appears to be this invisible substance. It is a galaxy where the dark universe completely overshadows the luminous one we see. How does such a thing come to exist? One theory casts these ultra-diffuse galaxies as cosmic failures. Imagine a vast cloud of primordial gas and dark matter beginning to collapse in the early universe. For a galaxy like the Milky Way, that gas cools, fragments, and ignites into a frenzy of star formation. But in a region like the Coma Cluster, the environment is brutally hostile. The space between galaxies is filled with a superheated plasma called the intracluster medium. If a nascent galaxy drifts through this searing fog, the intense heat can prevent its gas from cooling down. Without cool gas, stars cannot form. The dark matter halo collapses as planned, but the luminous galaxy within it simply never sparks to life, leaving behind a dark matter giant populated by only a faint, ancient sprinkling of stars. Another possibility is that these ghosts are the survivors of a violent stripping. A normal, star-rich galaxy could have wandered too close to the cluster's dense core long ago. The relentless gravitational tides and the pressure of the hot intracluster medium might have ripped away nearly all of its gas and a huge number of its stars, like a cosmic sandblaster scouring a stone. What remained was a dark matter core with a tenuous veil of the original stars, a galactic remnant stretched to an enormous, faint size. Yet Dragonfly 44 challenges even these explanations. Its dark matter halo is almost too massive and too intact for a simple stripping scenario, and its survival in the harsh cluster environment is itself a puzzle. These ultra-diffuse galaxies force us to ask fundamental questions about what a galaxy even is. Is the defining feature the stars we see, or the immense gravitational well of dark matter that holds it all together? They appear to be a distinct population, a shadow version of cosmic structure that our models did not predict. Each one is a silent rebuke to our assumptions, proving that the universe can build giants we can barely see, where darkness is not just present but overwhelmingly dominant. The dark matter giants of the cosmos exist in a sea of searing plasma, and that sea itself is scarred with impossible structures. Within the vast hot gas that fills the Virgo cluster, the Chandra X-ray Observatory has mapped something that defies common sense. It found cold fronts. This term is a cosmic misnomer, for these are not cold in any earthly sense. They are boundaries where gas at a mere 10 million degrees abruptly meets gas at a blistering 50 million degrees. Imagine dipping your hand into a pot of gently simmering water and instantly touching a region of molten steel with a razor-sharp line dividing the two. According to the basic laws of thermodynamics, such a stark difference should not last. In the turbulent, high-energy environment of a galaxy cluster, heat should diffuse rapidly, smoothing out any sharp boundary within a few 100 million years. Yet these cold fronts persist for billions of years, maintaining their crisp, shell-like edges as they plow through the intracluster medium. They are like perfect, undissolving ripples frozen in a cosmic pond. The existence of these fronts is a direct clue to the cluster's violent history. They are thought to be the aftermath of colossal mergers, created when a smaller group of galaxies plunged into the heart of the Virgo cluster. As this subgroup fell in, its own cloud of hot gas was rammed and compressed by the main cluster's even hotter atmosphere. This process, similar to a weather front in Earth's atmosphere but on a galactic scale, sheared and shaped the gas into vast, sliding layers with distinct temperatures. But the enduring sharpness of these fronts points to something more. Turbulence alone would have blurred them into oblivion eons ago. Something must be acting as an insulator, a cosmic barrier that prevents the hot and the super-hot gases from mixing. The prime suspect is magnetic fields. Threaded throughout the intracluster medium are vast, invisible lines of magnetic force. As a cold front moves, these magnetic fields can become stretched and amplified along its leading edge, forming a protective sheath. This magnetic layer effectively suppresses the microscopic processes that transfer heat across the boundary, acting like a perfect thermos wall in the depths of space. It keeps the sharp temperature difference intact, preserving a fossilized record of an ancient collision. Studying these fronts is like reading the rings of a tree, but for galactic catastrophes. Their curvature, their speed, and their stunning sharpness tell us not only that a merger happened, but how it happened, the angle of impact, the relative masses involved, and the astonishingly ordered physics that can emerge from chaos. They are silent, sliding monuments to violence, insulated by invisible forces we are only beginning to map. These sharp boundaries in hot gas are shaped by immense gravitational forces, but the very architecture of that gravity is now in question. Look at a massive galaxy like Messier 87 or Messier 49, and you will find a swarm of smaller satellite galaxies orbiting it, much like moons around a planet. According to our leading models, these satellites should be scattered randomly, orbiting in all directions from their host. They are thought to be ancient relics drawn in by the galaxy's dark matter halo, and such halos are predicted to be roughly spherical. The satellites, therefore, should be two, forming a chaotic, three-dimensional cloud. But that is not what we see. Instead, around several giant galaxies in the Virgo Supercluster, these satellites align themselves into startlingly thin, rotating planes. It is as if someone took a giant vinyl record, placed the massive galaxy at the center, and arranged all the smaller galaxies along the disk's edge. This is the plane of satellites problem, and it is a direct challenge to our understanding of how cosmic structures form. If dark matter halos are smooth and spherical, what force could possibly orchestrate dozens of independent satellite galaxies into such a neat, coherent disk? One possibility is that we are witnessing a statistical fluke, a cosmic coincidence that just happens to look organized from our particular viewpoint. But as more and more of these planes are discovered around different galaxies, the odds of it being a fluke grow vanishingly small. The alignment appears to be a real feature of the universe, not an illusion of perspective. A more compelling explanation lies in the ancient web of the cosmos. In the early universe, galaxies formed along dense filaments of dark matter and gas like beads on a string. It is possible that satellites were not captured randomly over time, but were born together along these primordial filaments. As the central galaxy grew, it could have drawn in this entire chain of satellite galaxies, preserving their original alignment in a single plane. They would be a fossilized snapshot of the cosmic filament that birthed them, all still orbiting in the same preferred direction billions of years later. This would mean the plane of satellites is not a mystery of gravity, but a memory of structure. Yet the most radical interpretation challenges the foundation of dark matter itself. Some scientists propose that the precise orbital planes could be evidence for modified gravity theories like MOND or modified Newtonian dynamics. These theories suggest that the effects we attribute to dark matter are actually a misunderstanding of how gravity works on galactic scales. In certain MOND models, the unique gravitational field around a massive galaxy could naturally channel smaller orbiting bodies into a disk-like configuration, potentially explaining the alignment without invoking invisible halos. This makes the planes a critical battleground between two competing views of the cosmos. Are we seeing the preserved architecture of creation, or the subtle signature of a law of gravity we have yet to fully write? Each thin, spinning disk of dwarf galaxies is a silent argument in a debate that reaches to the heart of physics. The precise planes of satellites suggest a universe of hidden order, but some cosmic structures seem to be nothing but ghostly potential. Scattered throughout the Virgo Supercluster are enigmatic clouds detected not by their light, but by their radio whispers. These are vast reservoirs of neutral hydrogen gas, the raw fuel for star formation, floating in apparent isolation. The most famous candidate is an object designated Virgo-I21, discovered by radio telescopes like the Lovell telescope at Jodrell Bank. It appeared as a significant, rotating cloud of hydrogen with no visible stars to account for its gravitational cohesion. For a moment, it seemed we had found the Holy Grail, a true dark galaxy, a structure made almost entirely of dark matter and primordial gas that never ignited into the fire of stars. The promise was intoxicating, a glimpse at a road not taken in cosmic evolution. Detecting these objects relies on the unique signature of neutral hydrogen atoms. When the spin of an atom's electron flips, it emits a faint radio wave at a very specific frequency. By tuning radio telescopes to this frequency and mapping where the signal comes from and how its wavelength is stretched or compressed, astronomers can not only find these gas clouds but also measure their rotation. In Virgo 21, the rotation was too fast to be held together by the gravity of the gas alone. An unseen mass, presumably dark matter, had to be providing the extra gravitational glue. This was the key evidence for a dark galaxy hypothesis, yet the story quickly grew complicated. The Virgo cluster is a dynamic, messy place full of gravitational interactions. A compelling alternative emerged. What if this cloud is not a failed galaxy, but the debris from a successful one? Powerful gravitational tides during close encounters between galaxies can stretch out immense streamers of gas, pulling them far into intergalactic space. This tidal debris can retain a coherent, rotating structure for a long time, mimicking the signature of an independent object. Detailed follow-up observations revealed that Virgo 21 lies near the galaxy M99, and its motion and position suggest it could be a tidal tail pulled out during a past interaction. The controversy highlights the delicate line between discovery and interpretation in modern astronomy. Is a rotating cloud of hydrogen with no stars a unique, dark matter-dominated entity, or is it simply the cosmic equivalent of a long, faint scar from a forgotten collision? The answer matters profoundly. If dark galaxies are real, they represent a whole population of cosmic building blocks that never switched on, challenging our models of how and why galaxies ignite. If they are all tidal debris, then they teach us instead about the violent choreography that continually reshapes the cluster. For now, each new hydrogen cloud discovered deep in the supercluster presents the same tantalizing, unresolved question. Are we looking at a ghost or just the echo of a past catastrophe? The hydrogen clouds drifting between galaxies face a brutal environment, a reality that spells doom for many. As galaxies orbit through the dense Virgo cluster, they plunge into a superheated sea of plasma known as the intracluster medium. This is not a gentle swim, it is a headlong rush against a hurricane. The pressure exerted by this searing gas is immense, and it acts like a cosmic wind, violently stripping a galaxy of its own cold hydrogen gas reservoir. This process is called ram pressure stripping. Picture a galaxy as a dandelion in a gale. The seeds representing the galaxy's precious star-forming gas are ripped away and scattered behind it. For most galaxies, this is a death sentence for new stars. Without its cold gas fuel, a galaxy cannot form new stellar generations. It becomes a red and dead relic, its population of stars slowly aging without renewal. This is the expected, tragic fate for many cluster galaxies. Yet the universe, in its infinite complexity, loves a paradox. Astronomers have observed galaxies in the very act of being stripped, their gas tails streaming behind them like cosmic comas. And within those tails, and sometimes even in the compressed disks of the galaxies themselves, they find something astonishing, not silence but a firestorm. In defiance of all logic, these galaxies are experiencing bursts of intense, anomalous star formation. It is as if the dandelion, while being blown apart, suddenly burst into brilliant new flowers along its trailing seeds. How can creation erupt from destruction? The answer lies in the physics of chaos. Ram pressure is not a gentle, even force. As the galactic gas cloud slams into the intracluster medium, it does not simply peel away smoothly. The interaction creates immense shock waves and turbulence within the gas itself. This violent compression can trigger the collapse of dense gas clouds that might otherwise have remained stable for eons. Think of it like squeezing a handful of snow. The pressure packs the flakes together tightly, and if you squeeze hard enough, you can form a solid, dense ice ball. In these galactic tails, the ram pressure is doing the squeezing, forcing pockets of gas to reach critical density and ignite into stars. Furthermore, the stripping process itself can funnel gas. As the outer layers of a galaxy's gas reservoir are stripped, the remaining gas in the disk can be driven inward, piling up in the central regions. This sudden influx of fuel into the galactic core can spark a frenzied burst of star formation there, a final, glorious blaze before the gas supply is completely cut off. These observations force us to rewrite the story of a galaxy's life in a cluster. It is not a simple narrative of slow starvation. Instead, it can be a dramatic, punctuated end, marked by one last, intense episode of stellar birth. The anomalous star formation tells us that the triggers for creation are more varied and violent than we knew. It reveals a universe where the very forces that tear galaxies apart can also, briefly, become the midwives for new suns. This firestorm in the wind is a testament to resilience, a final, brilliant act of cosmic defiance written in the light of newborn stars. That final blaze of star formation is a fleeting chapter, for the galaxies that survive the cluster's harsh environment grow old and quiet. Among the ancient red giants of the Virgo cluster are the elliptical galaxies, smooth, featureless spheres of aging stars. Their calm appearance, however, masks a violent history that should have left behind clear forensic evidence. These galaxies are dominated by old stellar populations, which means they should contain vast numbers of white dwarfs, the dense, Earth-sized cores left behind when sun-like stars die. And where there are white dwarfs, there should be cosmic explosions. When a white dwarf in a binary system steals enough matter from its companion or collides with another white dwarf, it can cross a critical mass threshold and detonate in a spectacular Type Ia supernova. These events are so uniform in their brightness they are used as cosmic mile markers to measure the expansion of the universe. Given the sheer number of old stars in a giant elliptical galaxy, astronomers predicted they should see a steady drizzle of these supernovae over cosmic time. Yet when they look for the aftermath, the evidence is strangely scarce. This is the supernova rate problem. Where are all the remnants? Using powerful X-ray telescopes like Chandra, scientists have scoured these galaxies for the telltale signs. A young supernova remnant is a brilliant X-ray source, its expanding shock wave heating surrounding gas to millions of degrees. But in ellipticals, the number of these bright, distinct remnants is far lower than the stellar census would suggest. One possibility is that our understanding of the explosions themselves is flawed. Perhaps the progenitor systems in these old, metal-rich environments are different. Maybe the white dwarfs are more likely to merge completely without a bright explosion, or the nature of the companion star alters the signature of the blast. Another, more practical explanation concerns the remnant's lifespan. In the sparse, hot gas that fills an elliptical galaxy, a supernova shock wave might expand rapidly into a low-density void. Without much material to sweep up and heat, the remnant could fade from view in X-rays much faster than it would in a gas-rich spiral galaxy. It becomes invisible to our telescopes long before the next one ignites, creating a gap in the record. The most profound answer, however, may lie in the galaxy's own histories. Could it be that these elliptical giants are not as uniformly old as they appear? If a significant fraction of their stars formed in a more recent, hidden burst of activity, the population of ready-to-explode white dwarfs would be smaller than we calculate. We might be misreading the demographic story written in their starlight. Each faint or missing remnant is a silent question about time and violence in these quiet giants. They force us to ask if we have misjudged the pace of stellar death, the physics of explosions in different environments, or even the true biography of the galaxies themselves. The answer is written in X-rays we cannot see, a hidden history of fire that has cooled into darkness. M86 is a galaxy in a screaming hurry. While most objects in the universe are receding from us in the general cosmic expansion, this giant elliptical is barreling toward the Milky Way at nearly 400 kilometers per second. Within the dense gravitational dance of the Virgo cluster, such a high velocity is not just unusual, it is a sign of a recent and dramatic event. This galaxy is a bullet fired through the heart of the cluster, and its trajectory holds secrets about the immense forces at play. The central mystery is the source of its incredible speed. One possibility is that M86 is a newcomer recently captured by the cluster's gravity. Imagine it falling in from the distant outskirts on a radial orbit, a near-perfect line aimed directly at the cluster's core. Like a comet falling toward the Sun, it will be accelerating under the immense collective pull of the cluster's dark matter and hundreds of galaxies, reaching a blistering pace by the time it passes near us. Its current path would then be a fleeting moment in a long, plunging orbit that will eventually swing it around the dense center and back out again. The other, more explosive explanation involves a close gravitational encounter with a true titan. M86's path has likely taken it near the supermassive galaxy M87, home to the famous relativistic jet. A close pass by such a massive object acts like a gravitational slingshot. The immense pull can dramatically alter a galaxy's course and speed, flinging it on a new, high-velocity trajectory. In this scenario, M86 is not just falling in, it has been kicked. The evidence for its violent journey is written across its form. As it races through the cluster's superheated intracluster medium, it is undergoing severe ram pressure stripping. Its own reservoir of cold gas is being violently torn away, streaming behind it in a vast, faint tail detectable in X-ray and radio observations. This tail is a cosmic contrail marking its path through the hostile environment. But the stripping is so extreme it has created a bow shock in front of the galaxy, a wave of compressed, heated gas like the prow of a ship plowing through water. Studying M86's precise motion and the shape of this disturbed gas allows astronomers to map the cluster's gravitational potential in a unique way. The galaxy is essentially a test particle moving through an invisible force field. By backtracking its path and measuring its velocity, scientists can infer the total mass, both seen and unseen, that must be pulling on it. It provides a dynamic check on the cluster's weight, independent of other methods. The high-speed plunge of M86 forces a question about its ultimate fate. Is this a one-way trip into the cluster's core, where it may eventually merge with another giant in a cataclysm of stars? Or is its velocity so great that it is on a hyperbolic escape trajectory, destined to be flung out of the cluster entirely, a galactic wanderer lost to the Intracluster void? Its journey is a snapshot of chaos, a reminder that even the most majestic structures are in constant, violent motion, driven by the silent, overwhelming pull of the dark universe. While M86 races through the cluster, it leaves behind more than just a trail of gas. Drifting in the immense blackness between the galaxies of Virgo are lonely ghosts, glowing shells of gas known as planetary nebulae. These are the final, beautiful shrouds cast off by dying sun-like stars, and they should, by all rights, be found only within the bounds of a galaxy. Yet here they are, isolated in the deep void, untethered from any stellar home. Each one is a cosmic orphan, and their existence poses a haunting question. How did these stars, which must have been born in the crowded nurseries of a galaxy, end their lives so far out in the emptiness? The leading explanation is one of violent ejection. The dense core of the Virgo cluster is a gravitational pinball machine. During close encounters between galaxies, the complex tidal forces can fling individual stars out into intergalactic space at tremendous speeds. This process, sometimes called galactic harassment, is a game of gravitational slingshots. A star orbiting peacefully in the outskirts of a small galaxy can receive a sudden, immense kick as its host galaxy swings past a more massive neighbor. The star is catapulted free, doomed to wander the cluster alone. Over billions of years, that exiled star ages in isolation. When its time finally comes, it sheds its outer layers in a gentle stellar wind, and the exposed hot core illuminates the expanding shell, creating a planetary nebula that glows for perhaps 10,000 years. We see it not as a death within a community, but as a solitary farewell in the dark. There is another, more radical possibility. Could these stars have formed right where they died, born from pockets of cold gas adrift in the intracluster medium? While the idea seems far-fetched, the cluster does contain vast, faint reservoirs of hydrogen. Under the right conditions of pressure and density, perhaps triggered by the shock waves of ancient mergers, some of this gas might have collapsed to form stars in the ultimate isolation. These stars would live and die without ever knowing a galactic home. Most astronomers, however, see the ejection theory as the more likely path. The numbers tell a compelling story. By carefully surveying for these faint, free-floating nebulae, scientists can actually trace the distribution of the intracluster starlight itself. Every planetary nebula they find marks the recent death of a single star, which in turn represents thousands of other, fainter stars that died long ago or are still shining unseen. The nebulae act like luminous buoys, mapping the unseen sea of orphaned stars that were stripped from galaxies during the cluster's violent formation. This makes them invaluable tools. By counting these ghosts, astronomers can measure how much stellar material was ripped out and flung into the void over the cluster's history. The pattern of their locations reveals the specific regions where gravitational encounters were most intense, painting a dynamic picture of the cluster's turbulent past. Each lonely, glowing shell is therefore a dual messenger. It speaks of a single star's quiet end, and it echoes the colossal, ancient violence that first set it adrift. They are the last, faint beacons of a scattered population, illuminating the hidden consequences of life in a crowded cosmos. The ghosts of exiled stars trace a history of scattering, but the galaxies left behind tell a story of a more systematic transformation. Look across the Virgo Supercluster and you will see a distinct cosmic pattern. In the dense heart of the Virgo cluster, the dominant galaxies are overwhelmingly red and dead, smooth ellipticals with ancient stellar populations. Their star-forming days ended long ago. This is not a local oddity, but part of a universal trend known as the Butcher-Ohmler effect. Decades ago, astronomers Harlan Butcher and Augustus Ohmler made a startling discovery. When they looked at galaxy clusters much farther away, and thus seen as they were billions of years in the past, they found a dramatically different picture. Those ancient clusters were filled with blue, spiral galaxies actively forming new stars. The modern, nearby clusters like Virgo are dominated by this red sequence of quiescent galaxies. The universe, it seems, has been running a cosmic factory that takes in blue, star-forming spirals and outputs red, dead ellipticals. The Virgo cluster is our closest laboratory to dissect how this factory works. The central, unresolved question is one of efficiency. What physical process or combination of processes is so effective at quenching star formation, at shutting down a galaxy's engine of creation as it becomes part of a cluster? The prime suspect is the same brutal force that can sometimes trigger a final starburst, ram pressure stripping. As a spiral galaxy falls into the cluster, the superheated intracluster medium acts like a sandblaster, violently removing its cold hydrogen gas, the raw fuel for new stars. This is a rapid and dramatic shutdown, a galactic strangulation by force. You can see its evidence in galaxies with gas tails streaming behind them, their star formation flickering out. But there is another, more subtle killer known simply as strangulation or sometimes starvation. This occurs when a galaxy's extended reservoir of gas, the halo that would normally replenish its disk over time, is cut off. As the galaxy enters the cluster environment, this external fuel supply is stripped away or heated to the point it can no longer cool and fall in. The galaxy then consumes its remaining internal gas, forming stars until the tank is empty. This leads to a slower, more gradual quenching, a fading rather than a violent end. Then there are the transformative mergers, when two gas-rich spiral galaxies collide and merge in the cluster's dense environment. The event can trigger a ferocious burst of star formation that rapidly consumes the available gas. The resulting galaxy after this explosive finale is often an elliptical, its gas spent, its star formation over. This is a quenching by glorious excess. The great mystery in Virgo is determining which of these scripts is most common. Is the transition from blue to red primarily a story of rapid external violence, a slow internal starvation, or a transformative collision? The answer likely involves all three, acting on different galaxies at different times. By studying the precise states of Virgo's galaxies, astronomers look for clues. They measure the remaining gas in spirals on the cluster's outskirts versus those near the core. They map the ages of stars in ellipticals to see if they all shut down at once or in staggered waves. Each galaxy is a fossilized record of its own quenching event. Understanding this cosmic assembly line is crucial because it dictates the life cycle of most of the universe's stars. The red sequence in Virgo is not just a collection of old galaxies. It is the final product of a billion-year process, the quiet endpoint of a drama that shaped the universe we see today. What silenced these giants is a question whose answer lies in the delicate balance between a galaxy's own resilience and the relentless pressures of a crowded cosmos. The red sequence of silent galaxies holds a secret in its heart. Within many of these quiet giants, including our own Milky Way, the central supermassive black hole is not truly dead. It is dormant, flickering with a faint but persistent glow. These are low-luminosity active galactic nuclei, or LLGN, and they represent the most common state for these cosmic monsters. Across the Virgo Supercluster, from M87 to M61, these faint central engines are everywhere. Their quietness, however, is the real puzzle. If a supermassive black hole is surrounded by a feast of gas and stars, why is it only nibbling? The leading theory points to a radical change in how the black hole dines. In brilliant quasars and luminous active galaxies, gas forms a thin, hot, and efficient accretion disk as it spirals inward. This disk is like a well-organized conveyor belt delivering food directly to the black hole's maw, releasing enormous amounts of light in the process. But for a low-luminosity active nucleus, the menu may be completely different. The gas falling toward it might be too hot and too tenuous to form that neat, efficient disk. Instead, it could form a puffy, diffuse cloud where particles are so spread out they rarely collide and radiate energy. This is called an advection-dominated accretion flow. In this mode, most of the gravitational energy is simply swallowed by the black hole along with the gas, rather than being converted into the brilliant light we associate with quasars. It is the difference between a roaring, efficient furnace and a smoldering, smoky fire that gives off little heat. This faint state may be intimately connected to the very process that quenches a galaxy. As a galaxy evolves and its star formation is strangled, the supply of cold, dense gas to the central black hole is also cut off. The black hole is left to subsist on a meager diet of hot, ionized gas from stellar winds or the occasional shredded star. It enters a long, quiet phase of advection-dominated accretion, its faint glow a sign of a starving giant. This creates a profound feedback loop. The black hole's low luminosity output, often in the form of gentle jets or wide-angle winds, can still inject energy into the surrounding galaxy. This gentle heating helps keep the remaining gas hot and prevents it from cooling and collapsing to form new stars, thereby helping to maintain the galaxy's red and dead status. The low-luminosity active nucleus is not just a passive relic, it is an active participant in preserving the galaxy's quiescence. The prevalence of these faint engines across Virgo forces a fundamental question about cosmic history. Is the dazzling quasar phase with its incredible luminosity just a brief, adolescent outburst in a black hole's life, a fleeting frenzy of consumption after a major merger? Is the long, quiet eon of low luminosity accretion the true adult state of these giants, a sustained whisper that does more to shape a galaxy's fate than its brief, brilliant shout ever could? The silent hearts of Virgo galaxies are not inactive. They are ticking over slowly, governing their realms with a faint but steady hand, their quiet power written into the very stillness of the stars around them. That faint, governing glow from dormant black holes is a local phenomenon, but our entire neighborhood is caught in a far grander motion. Our Milky Way, along with the entire local group of galaxies, is not simply drifting with the cosmic expansion. We are on a specific, high-speed journey, pulled by titanic gravitational forces on a scale almost beyond comprehension. First and foremost, we are falling toward the dense heart of the Virgo Supercluster itself, accelerating toward the mass of the Virgo cluster at over 200 kilometers per second. This makes intuitive sense. We are being drawn toward the greatest local concentration of matter. Yet when astronomers subtract that predictable pull, a startling fact remains. Our motion does not stop or even slow significantly. We, along with the Virgo supercluster itself, are still streaming in a specific direction at over 600 kilometers per second toward a point in the constellation Centaurus. Something even more massive than the entire Virgo supercluster is pulling us. This is the Great Attractor, a gravitational focal point that represents one of the most significant anomalies in modern cosmology. For decades, this region was profoundly difficult to study because it lies directly behind the plane of our own Milky Way, hidden by thick clouds of interstellar gas and dust, an area astronomers call the zone of avoidance. It was a blind spot in our cosmic map, masking a colossal mystery. With the advent of infrared and radio telescopes that can peer through the galactic veil, we have begun to map the hidden architecture. We now see that the Great Attractor is not a single, incomprehensibly dense object, but rather the core of a vast supercluster of galaxies, now called the Laniakea Supercluster, of which Virgo is merely an appendage. Its gravitational center lies near the Norma cluster, a dense knot of galaxies, but the story does not end there. Even after accounting for the pull of Laniakea's immense mass, a residual motion persists. Our entire local universe appears to be flowing toward something even more distant and more massive, the Shapley Supercluster, the largest known concentration of matter in the observable universe, located over 600 million light-years away. This vast, coherent stream of galaxies across billions of light-years is called the bulk flow, and here lies the core of the anomaly. When we tally up all the visible and dark matter in the Laniakea and Shapley superclusters and account for the repulsive effect of dark energy, our models still cannot fully explain the observed speed and direction of this bulk flow. The universe, on its largest scales, seems to be moving faster than the mass we can map should allow. This discrepancy forces a profound question. Are we missing even larger, more distant structures whose gravity is still tugging on us? Structures so vast and faint they blend into the cosmic background. Or does this persistent motion point to a potential flaw in our standard model of cosmology? Perhaps dark energy is not perfectly uniform, but varies in strength across space, creating unexpected currents in the fabric of the cosmos. Maybe our understanding of how gravity works over these immense inter-supercluster distances needs refinement. Each possibility opens a door to a radically different universe. The Virgo supercluster's motion anomaly is therefore more than a curiosity about our direction of travel. It is a cosmic speedometer whose reading does not match our map of the road. It suggests that the true architecture of the universe extends beyond even the grandest webs we have charted, and that the forces shaping our journey may be more complex and more mysterious than we have yet dared to imagine. The great cosmic current pulling our supercluster hints at immense hidden structures, but within the Virgo cluster itself, astronomers have stumbled upon objects so dense they defy simple classification. They are called ultra-compact dwarfs, and they are cosmic conundrums packed into a tiny, brilliant point. Discovered only in the last few decades, these objects look at first glance like particularly bright globular clusters, the ancient spherical swarms of stars that orbit galaxies like cosmic bees around a hive. But a closer look reveals something profoundly different. An ultra-compact dwarf is only about 100 light-years across, roughly the distance from our Sun to its nearest stellar neighbors, yet it can contain tens of millions of stars. This gives it a stellar density thousands of times greater than a typical globular cluster. It is a stellar metropolis crammed into a volume smaller than many cities, a place where stars are separated by mere light weeks instead of light years. The central mystery is their origin. What cosmic process could forge such an absurdly dense stellar system? One compelling theory casts them as the grim survivors of a violent stripping. Imagine a small, normal dwarf galaxy wandering too close to a giant like Messier 87. The immense gravitational tides could rip away over 99% of its stars, scattering them into the intracluster light. All that remains is the galaxy's dense central nucleus, a core of stars so tightly bound they withstand the catastrophe. This stripped nucleus, left to orbit the giant galaxy alone, would appear to us as an ultra-compact dwarf. It is a galactic ghost, the beating heart of a galaxy whose body has been torn away. The alternative is that they are simply the upper limit of something familiar, supermassive globular clusters. Perhaps in the rich early environment of the cluster, some globular clusters formed with exceptionally high masses from the start. They would be born giants, not made through violence. The evidence, however, is tipping the scales toward a more dramatic origin. Some ultra-compact dwarfs have been found to harbor a secret at their center, a supermassive black hole. This is a feature utterly unexpected in a globular cluster, but perfectly logical for the remnant core of a galaxy, as galaxies and their central black holes grow together. Finding that dark anchor of mass is like finding a skeleton key. It unlocks the object's true identity as a galactic nucleus in hiding. Furthermore, their chemical makeup often shows they are enriched with heavier elements, suggesting they formed from gas that had already been cycled through multiple generations of stars, another hallmark of a true galaxy rather than a simple primordial star cluster. These objects force us to redraw the boundaries of our cosmic categories. They exist in a strange middle ground, too massive and complex to be mere star clusters, yet too small and dense to be traditional dwarf galaxies. Each ultra-compact dwarf is a fossil of a specific type of cosmic violence, a trophy collected by a giant galaxy, proving that in the crowded core of a cluster, even galaxies can be skinned to their bones. Their brilliant, compact light is a beacon from a forgotten catastrophe, a final, dense testament to a structure that once was far grander. The ultra-compact dwarfs are dense survivors of a violent past, but at the very heart of the Virgo cluster, a different kind of survival is taking place. A delicate balance of cosmic forces is preventing a catastrophe of creation. Deep within the core of the cluster, surrounding the giant galaxy M87, the intracluster gas reaches temperatures of tens of millions of degrees. This superheated plasma glows brilliantly in X-rays, a testament to its immense energy. According to straightforward physics, this gas should be cooling down. As it radiates away its energy in the form of X-rays, it should lose pressure, causing the cooler, denser gas to sink inward toward the cluster's gravitational center. This inward flow, known as a cooling flow, was a major prediction for clusters like Virgo. The numbers were staggering. Calculations suggested that hundreds of solar masses of gas should be cooling and flowing into the central galaxy every single year. This vast river of cold fuel should have triggered an epic burst of star formation. turning M87 into a stellar factory of unimaginable scale, surrounded by countless young star clusters and glowing nebulae. Yet when astronomers look, they see none of it. The predicted deluge of new stars is simply absent. This glaring mismatch between theory and observation is the cooling flow problem. Where did all that cooling gas go? The leading answer points to a counterintuitive source, the monster at the very center of the crisis. The supermassive black hole in M87, while often in a low luminosity state, is not silent. It is actively fighting the cooling process through a mechanism called active galactic nucleus feedback. As small amounts of gas fall toward the black hole, they power gentle jets and wide-angle winds that inject tremendous energy back into the surrounding hot gas. This is not the violent, focused blast of its famous relativistic jet, but a more diffuse, persistent heating. It acts like a cosmic thermostat. When the gas begins to cool and condense, it provides more fuel for the black hole. The black hole then becomes slightly more active, its output increasing just enough to reheat the gas and shut off the fuel supply. This prevents a runaway cooling collapse. The process is a beautiful example of self-regulation, where the predator controls the population of its prey to ensure its own long-term survival. However, the precise mechanics of this feedback loop remain one of the great unsolved puzzles. How is the energy from the black hole so perfectly coupled to the gas on such vast scales? The energy must be transferred efficiently, without simply blasting the gas away entirely or leaving cold pockets untouched. It appears to work through a combination of gentle shock waves, turbulence, and sound waves that ripple through the intracluster medium, distributing the heat like a spoon stirring a giant cup of coffee. But the details are maddeningly complex. Why doesn't the feedback sometimes overshoot, overheating the core and completely shutting off the black hole's own fuel source? How does it avoid undershooting, allowing those forbidden cooling flows to briefly ignite? The system operates with a precision that our best computer simulations still struggle to replicate. This isn't just about a missing river of gas, it's about understanding a fundamental governing principle of cosmic ecosystems. The absence of a cooling flow reveals a universe where the most destructive objects, supermassive black holes, have become the guardians of order. They enforce a stable, quiet middle age for giant galaxies, preventing them from either burning out in a frenzy of star formation or freezing over into a cold, dark state. The quiet center of the Virgo cluster is not a passive scene. It is a standoff, a billion-year negotiation between the irresistible pull of gravity and the formidable feedback from a dark heart, maintaining a precarious and silent peace. That delicate balance in the cluster's core is maintained by a chemical legacy written into the superheated gas itself. The intracluster medium is far from a pristine, primordial soup. When astronomers analyze its X-ray spectrum, they find the unmistakable signatures of heavy elements like iron, oxygen, and silicon. These are metals forged in the nuclear furnaces of stars and scattered into space by supernova explosions. The sheer abundance is startling, with the total mass of iron floating in Virgo's hot gas alone equaling that of many billions of suns. This presents a profound logistical mystery. How did the products of countless stellar deaths become so thoroughly and evenly mixed into a sea of gas that fills millions of cubic light-years? The process of cosmic pollution on this scale is a story of immense force and patient time. One primary delivery mechanism is galactic winds. When a galaxy experiences a burst of star formation, the combined effect of stellar radiation and the shockwaves from supernova can drive powerful outflows, literally blowing metal-enriched gas out of the galaxy and into the surrounding void. Think of it as a city's factories belching smoke into the atmosphere, but on a galactic scale. These winds provide a steady, widespread drizzle of enriched material. More dramatic are the contributions from active galactic nuclei, the supermassive black holes at the hearts of galaxies. Their energetic jets and winds can act like cosmic pressure washers, scouring metal-rich gas from a galaxy's core and ejecting it at high speeds, capable of reaching the farthest corners of the intracluster medium. This process doesn't just pollute, it stirs. The energy from these events creates turbulence, churning the hot gas and helping to distribute the metals more uniformly, preventing them from simply clumping around their source galaxies. Yet the most intriguing clue comes from the chemical composition itself. The ratios of different elements in the intracluster gas don't perfectly match what we'd expect if all the enrichment happened recently. There's evidence for an ancient foundational layer of pollution. This points to a period known as pre-enrichment, occurring long before the Virgo cluster took its modern shape. In the early universe, the first generations of stars, known as population 3 stars, were likely monstrous giants that lived fast and died young in spectacular supernova. These titanic explosions would have seeded the primordial gas with the first heavy elements. When galaxy clusters later formed from this pre-polluted material, their intracluster medium started with a baseline level of metals already in the mix. The chemical history we read in the hot gas today is therefore a layered archive. It records the quiet, early enrichment from the universe's first stars, overlaid with the more recent, violent contributions from galactic winds and black hole feedback. Unraveling this history is like analyzing the sediment layers at the bottom of an ancient ocean, each stratum telling of a different climatic era. The strange chemistry of the intracluster gas forces us to see the supercluster not as a static collection of islands, but as a single, interconnected ecosystem. Stars are born, live, and die within galaxies, but their legacy, the very elements they forge, ultimately escapes to fill the vast spaces between, linking every galaxy in a shared chemical heritage. The hot plasma is the supercluster's circulatory system, and flowing within it is the elemental proof that nothing in this cosmic web truly exists in isolation. These heavy elements are a testament to the supercluster's shared history, but some of its oldest witnesses travel that history alone. Drifting through the immense darkness between the galaxies of Virgo are ancient spherical cities of stars known as orphan globular clusters. Unlike the vast majority of their kind, which orbit securely within the gravitational embrace of a single galaxy, these clusters are free agents. They are bound not to M87 or M49, but to the entire gravitational potential of the Virgo cluster itself, tracing wide, lonely orbits through the intergalactic void. Each one is a relic of the earliest cosmic days, a compact ball of up to 1 million stars that formed when the universe was young. Their present isolation, however, poses a deep puzzle of origins. How did these ancient stellar systems become untethered? Two compelling, competing stories explain their solitude. The first is a tale of galactic violence and loss. As galaxies collide and merge within the dense cluster, the immense gravitational tides can act like cosmic hands, plucking globular clusters from the outer halos of their host galaxies and flinging them into the abyss. In this scenario, an orphan cluster is a refugee, a survivor stripped from its home during a catastrophic encounter billions of years ago. Its current, independent orbit is a permanent record of that ancient theft. The other story is one of primordial independence. Perhaps these clusters never belonged to a galaxy at all. In the early universe, small clumps of dark matter, known as subhalos, may have collapsed and collected enough gas to ignite a burst of star formation, creating a globular cluster. If that dark matter halo was later stripped away or never grew massive enough to attract more gas and become a true dwarf galaxy, the cluster would be left as a bare stellar system, orbiting the larger cluster potential from the very beginning. It would be not an orphan, but a cosmic foundling born free. Determining which story is true for any given orphan cluster is a forensic challenge. Astronomers look for clues in their chemical composition and their orbits. A cluster that was stripped from a large galaxy like M87 might carry the chemical signature of that galaxy's more complex star-forming history, showing higher levels of heavier elements. A primordial cluster formed in isolation from pristine gas might have a simpler, more ancient chemical fingerprint. The paths they travel are also telling. Clusters stripped from galaxies on radial plunges into the cluster core might be found on similar plunging orbits, while primordial clusters could have more varied, random trajectories that reflect the chaotic conditions of the cluster's formation. These wandering stellar cities are more than just curiosities. They are tracers of the cluster's assembly history. By mapping their locations and motions, astronomers can reconstruct the gravitational tides that have shaped Virgo over billions of years. A large population of orphans would be strong evidence for a violent, merger-heavy past where galaxies were routinely torn apart. Their very existence tests the efficiency of tidal stripping, showing us just how thoroughly the cluster's giants can dismantle their smaller neighbors. Each lonely, ancient globe of stars is a silent vote in the debate over how our cosmic neighborhood was built, piece by violent piece, from the raw materials of the early universe. These wandering stellar cities map a history of ancient violence, but at the very center of that history, a faint, invisible whisper fills the space. Encircling the giant galaxy M87 is a vast, diffuse cloud of radio emission known as a mini-halo. This is not the brilliant, focused beam of the famous jet, but something far more subtle and enigmatic. It is a faint radio glow millions of light years across, permeating the hot gas at the cluster's heart. Its very existence is a puzzle, for such a structure should not be able to persist. The electrons responsible for this synchrotron radiation, spiraling around magnetic field lines at near light speed, lose their energy incredibly fast. Within 100 million years, they should have radiated all their power away and faded into silence. Yet the mini-halo shines on, a clear sign that some hidden engine is continuously re-energizing these particles, pumping them back up like a cosmic battery that never drains. The central question is, what is that engine? Two competing forces are at play. The first is turbulence from the cluster's violent formation. As galaxies and groups fell into the Virgo cluster over billions of years, their mergers would have sent powerful shockwaves rippling through the intracluster medium. This ongoing chaos could stir the magnetic fields and act as a giant particle accelerator, continually giving electrons a fresh boost of energy. In this model, the mini-halo is a fossilized echo of the cluster's tumultuous assembly, its faint glow powered by the lingering vibrations of ancient collisions. The other suspect sits at the very center of the glow, the supermassive black hole itself. While its dramatic jet points in one direction, the active galactic nucleus might also be driving gentler, wider outflows. These outflows could create sound waves and weak shocks that travel through the core, effectively re-accelerating the old population of electrons that would otherwise have faded. Here, the mini-halo would not be a relic of past mergers, but a living testament to the ongoing, subtle feedback from the central black hole, a secondary effect of its governing presence. Distinguishing between these models is a monumental challenge for astronomers. The radio emission itself looks smooth and diffuse, offering few direct clues to its power source. Scientists must instead look for correlations. Does the shape and size of the mini-halo align with known shock fronts from past mergers seen in X-rays? Or does its structure seem more intimately connected to the immediate environment of M87's core? They also hunt for very specific signatures in the radio spectrum, subtle tilts or curves in the emission that could betray whether the electrons were accelerated in a single, powerful event or through a continuous, gentle process. Beyond its origin story, the mini-halo is a unique probe of invisible physics. Its very presence tells us that the intracluster medium is threaded with magnetic fields, faint but pervasive, providing the tracks along which the high-energy electrons spiral. By studying the halo's properties, astronomers can indirectly measure the strength and structure of these magnetic fields. mapping forces that are otherwise completely undetectable. Furthermore, it reveals that particle acceleration, a process we often associate with the most violent explosions, is happening quietly and continuously in what appears to be a calm, hot plasma. This faint radio whisper forces us to listen more carefully to the cluster's core. Is the dominant sound the fading drumbeat of ancient collisions, or the steady, low hum of a central black hole's heartbeat? The answer will tell us whether the energy shaping the cluster's heart comes primarily from its violent history or from the persistent, governing influence of the dark giant at its center. The mini-halo is a ghostly signature of power, and we are still learning whose hand is writing it. The faint radio glow of the mini-halo is a whisper of power, but the true census of the supercluster's smallest citizens is still being taken. According to our most sophisticated computer simulations of cosmic structure, the Virgo Supercluster should be teeming with a vast population of faint dwarf galaxies. These tiny stellar systems, each holding perhaps only a few million stars, are predicted to be the most common type of galaxy in the universe. They are the cosmic equivalent of a vast, unseen population of small towns, far outnumbering the great metropolises like the Milky Way. Yet when astronomers conduct deep surveys of the Virgo cluster, carefully counting every faint smudge of light, the numbers do not add up. Observations have not found nearly as many of these faint dwarfs as the simulations insist should be there. This mismatch is known as the dwarf galaxy luminosity function problem, and it represents a critical stress test for our entire theory of how galaxies form. Where are all the missing dwarfs? One straightforward answer is that they are simply too faint for us to see. Our telescopes have limits. A dwarf galaxy with very few stars and spread over a large area can have a surface brightness so low it blends perfectly into the natural glow of Earth's own night sky. Detecting these ultra-faint systems is like trying to spot a single, distant firefly against the backdrop of a lit city. It requires incredibly deep, patient surveys with the world's largest telescopes, and even then, we might only be seeing the very brightest tip of a vast, hidden iceberg. Every improvement in camera technology and data processing reveals a few more of these ghostly objects, but the gap between prediction and observation stubbornly persists. Perhaps the dwarfs are not hiding, but were never born at all. This leads us to a pivotal moment in cosmic history called the epoch of reionization. In the first few 100 million years after the Big Bang, the universe was filled with a fog of neutral hydrogen gas. Then the first stars and galaxies ignited, their intense ultraviolet radiation beginning to ionize this fog, burning it away and making the universe transparent. This process of reionization was a cosmic dawn, but it may also have been a cosmic culling. The ultraviolet radiation flooding the early universe could have heated the gas in the smallest, faintest dark matter halos, preventing it from ever cooling down and collapsing to form stars. In this scenario, the smallest dwarf galaxies were stillborn. Their dark matter halos exist as the simulations predict, but they are devoid of stars, invisible to our optical telescopes. They would be true dark galaxies, contributing to the missing count. A third, more profound possibility is that our understanding of dark matter substructure itself is incomplete. The simulations that predict this vast dwarf population are based on the cold dark matter model, where dark matter particles move slowly and interact only through gravity. This model beautifully reproduces the large-scale cosmic web, but what if it gets the small-scale details wrong? Perhaps dark matter has some intrinsic property, a tiny amount of warmth or a capacity for self-interaction that suppresses the formation of the very smallest halos. If the underlying dark matter scaffolding is different than we assume, then the expected population of tiny halos that could host dwarf galaxies might be far smaller. The missing dwarfs, then, would be a ghostly clue pointing toward a richer physics of the dark universe. This is not just an accounting error. The dwarf galaxy luminosity function is a direct probe of the conditions in the early universe and the nature of the invisible matter that shapes it. Each faint dwarf we do find is a survivor, a system that somehow managed to form stars against the odds. By studying their properties, their locations, their shapes, their chemical makeup, we can begin to piece together what allowed them to succeed where so many others seemingly failed. Were they simply born in slightly denser patches of the primordial gas? Did they form their stars quickly before the harsh ultraviolet radiation of reionization could sterilize them? Or do they orbit in protected environments, sheltered from the full brunt of the cluster's destructive forces? The quiet, faint light of each dwarf galaxy is a message from a frontier, a testament to a struggle for existence on a cosmic scale. Their absence is as loud as their presence, a silent question written across the vast darkness of the supercluster. The faintest dwarfs may be missing, but the space between them is threaded with invisible lines of force. Radio telescopes have mapped a structure of breathtaking scale, revealing that the entire Virgo cluster is woven through with vast, coherent magnetic fields. These are not the tangled, chaotic fields confined to single galaxies, but ordered patterns that stretch across millions of light years, aligning with the cluster's very architecture. We detect them through a subtle signature in radio waves known as polarized emission. As fast-moving electrons spiral along these cosmic field lines, they emit radio light that vibrates in a specific direction, like sunlight glinting off the surface of a lake. By collecting this polarized whisper, astronomers can trace the shape and strength of magnetic fields in the deepest void. The sheer scale of this organization presents a profound mystery. How did magnetic fields, which we typically think of as local phenomena tied to stars or galaxies, become so immensely strong and so perfectly ordered across an entire cluster of galaxies? The energies involved are staggering, defying any simple explanation. One compelling theory begins at the dawn of time. The universe may have been born with weak, primordial seed fields, infinitesimal magnetic threads woven into the fabric of space itself during its earliest, most energetic moments. These seeds would have been unimaginably faint, but as the Virgo cluster formed over billions of years, it provided a cosmic engine for amplification. The process is one of violent motion and patient stretching. As galaxies and groups fell into the growing cluster, their collisions and mergers created immense turbulence in the hot intracluster gas. Think of a vast, slow-motion whirlpool, but one filled with searing plasma. This turbulence would have stretched, folded, and twisted those primordial magnetic lines, a process scientists call dynamo amplification. Much like a child twisting a rubber band to make it tighter and more tense, the chaotic motions of the cluster's birth could have systematically strengthened the weak seed fields by orders of magnitude, weaving them into the large-scale patterns we see today. It is a story of chaos giving birth to order, of random motions sculpting invisible threads across cosmic time. Yet there is another powerful force at work, one that writes magnetic structure from the inside out. Galactic outflows provide a continuous source of new magnetic material. When a galaxy experiences a starburst or its central black hole becomes active, it can blow colossal winds of magnetized plasma out into intergalactic space. These outflows act like cosmic looms, injecting organized magnetic fields directly into the cluster environment. As these magnetized bubbles expand and collide, they can merge and align, gradually building up the large-scale coherence from countless smaller contributions. The magnetic fields we observe today are likely a hybrid, a palimpsest written by both ancient and modern processes. The primordial seeds provided the initial canvas, amplified by the turbulence of the cluster's violent youth, and then continuously enriched and reordered by the breath of its member galaxies across eons. This discovery transforms our view of the intracluster medium. It is not a passive hot fog, but a dynamic, magnetized fluid. These large-scale fields have profound consequences. They influence how heat travels through the cluster, potentially explaining the sharpness of the cold fronts. They govern the acceleration and confinement of the high-energy particles that create the faint radio mini-halo. They may even affect the very growth of galaxies by regulating the flow of gas. The existence of such ordered magnetism on a supercluster scale hints at a universe deeply interconnected by forces beyond gravity. It suggests that the empty spaces are not truly empty, but structured by invisible architectures of power, built by the combined history of everything they contain. The silent spaces between the galaxies are alive with a hidden order, a magnetic memory of all that has moved within them. From the ghostly intracluster light to the magnetic fields spanning millions of light years, each of these 25 phenomena is far more than a cosmic oddity. They are active frontiers. The missing baryons and the Leo ring challenge our inventory of the universe's basic building blocks. The core cusp problem and the planes of satellites probe the very nature of dark matter, forcing us to choose between complex astrophysics and new fundamental laws. The Butcher-Ohmler effect and the quenching of galaxies reveal the life and death cycles of cosmic cities, while the cooling flow paradox and the faint glow of low-luminosity active nuclei show how black holes govern their domains with silent feedback. The high-speed plunge of M86, the orphan globular clusters, and the faint planetary nebulae drifting in the void are all testaments to a violent, dynamic history written in motion. Anomalies like the overweight black hole in NGC 4472 and the impossible star formation within RAM pressure tails remind us that nature always finds a way to defy our simplest expectations. Even the empty quiet of the Fornax Void and the great current pulling our entire supercluster are clues to the architecture of reality on its grandest scales, hinting at dark energy's role and masses beyond our maps. Together, they form a single, interconnected mystery. The Virgo Supercluster is not merely a place we observe from a distance. It is our local laboratory, a cosmic backyard where the universe has set up its most confounding experiments within reach of our telescopes. Every unanswered question is an invitation. The next time you look up at the night sky, remember that you are gazing into the heart of this vast, mysterious neighborhood. The search continues with every observation from the James Webb Space Telescope, the Chandra X-ray Observatory, and the next generation of giant telescopes being built on mountaintops around the world. They are all turning their gaze toward these puzzles, collecting the light that will one day, piece by piece, reveal the answers. Which of these 25 unexplained phenomena captured your imagination the most? Was it the dark matter fortress of Dragonfly 44, the primordial mystery of the Leo ring, or the silent governing power of a black hole's whisper? Share your thoughts below and let us keep looking up together into the great unknown.